Okay, we are now in chapter 8. So, chapter 8 is about the interactive forces. Okay, so in the seventh chapter, we have discussed that the static atomic arrangement. Okay, so in chapter 8, we're going to examine how do all the atoms been bond together. Okay, so why are they static and what actually bond all these atoms together? So the very first question that I would like to start with this chapter is what hold a crystal together? We know that the crystal composed of many atoms, okay, but with the proper atomic arrangement. And why do all these atoms been arranged in charge arrangement? Okay, what actually hold all the atoms together and form the crystal? So in this chapter, uh, we will study the interatomic forces as well as explain it using the Pauli principle. Okay, so a very simple answer to this question is that the atom bind together due to the Coulomb attractive and repulsive forces between electron, neighboring atomic ion, and nuclei. Okay. So first of all, I would like to introduce you to the crystal binding. We know that the solid are the stable structure. Stable means that the atoms not free to move, and they can only move with the limitation. That means that they can vibrate. All right, and therefore there exists some interaction holding the atom in a crystal together. So later on we'll discuss what are these interaction. The arrangement of atom in a solid can be of many different types, even for the same material, like what we have discussed before, the polymorph. So even the same material like copper, it can form different type of the atom arrangement. It can form HCP, it can form FCC, and so on and so on. So when they form different atom arrangement, then definitely they will have different bonding. All right. So its formation depends on the external parameter such as the temperature, pressure, and the role in the phase diagram, which is followed during the transition. For the example, from liquid to solid. So uh, for the copper, when you melt it, okay, you melt the copper or you melt the zinc or iron. You melt it and then you let it cool down, and then you let it cool down with different temperature or different pressure, then they will follow the different road in the phase diagram. So when they form the crystal, they have the possibility that the atom will arrange in different arrangement with the previous one before it melt. Okay, so when this happen, then the atom actually been hold by different type of the bonding. So there are some important internal parameter that we will need to take into consideration, such as the electronic configuration of the atom, the atomic ionic radii, which also determine the nature and strength of the binding between the atoms. Okay, so now this is for crystal binding. Sodium chloride crystal is more stable than group of free sodium and chloride atoms. Why? Okay, I will give you 10 seconds to think about it. Okay, sodium chloride crystal is more stable because they have less energy. Whenever the material or the molecule or whatever thing have less energy, that means that they are more stable. Okay, minimum energy means they are stable. When like we have the separated sodium and chloride atom, when they are free, they are free. Why they are free? Because they have high energy. Okay, whenever they have high energy, then they will be less stable. Okay, so the condition for the stability of a crystal is given as cohesive energy equal to free atom energy minus crystal energy. Okay, the cohesive energy is defined as the energy required to break the atom of the solid into isolated atomic species. That means that, let's say you have one crystal. Okay, so if you want to break all the atom inside the crystal into the separated one, then you need to apply the energy, right? How much energy is required? It depends on this term, cohesive energy. Okay, so let's say the cohesive energy is 446 kilojoule per mole for silicon. Then if you want to separate the silicon atom or silicon crystal into the silicon atom, then you need to provide 446 kilojoule per mole of the energy. Okay, so basically the cohesive energy is defined as free atom energy minus crystal energy. Okay, so basically it's very simple. So we know that at the crystal, let's say this is the silicon at the crystal, let's say it have the energy of x energy. Then when you break it, now you have all the silicon which are freely moved. Then now you have y energy. So if I ask you what is the energy required to break the silicon crystal into individual silicon atom, then the answer will be y minus x, right? So the energy of the free atom minus the energy of the crystal of the silicon. Therefore, the definition for the cohesive energy equal to free atom energy minus crystal energy. Okay, so here we have two examples. The first example is silicon. The cohesive energy is 446 kilojoule per mole. Then we can consider that this is a strong strength of binding. However, for argon, the cohesive energy is just 7.74. So we can say that the strength of binding of the argon is very, very, very weak. That means if you want to break the bond of all the argon into the individual one, then you only need to apply 7.74 kilojoule per mole of the energy. However, if you want to break the silicon crystal into the small pieces of the individual silicon atom, then you need to provide 446 kilojoule per mole of the energy. Okay, so again, the cohesive energy basically is just the energy required to break the atom of the solid into the isolated atomic species. Okay, from the collectively one, the crystal break into the isolated one, the individual one. Okay, so this is a cohesive energy. And now I told you just now, if I ask you to calculate the equation, very simple. The free atom energy, the isolated atomic species, minus the solid, the crystal. Okay, so this free atom energy basically is referring to the energy of the isolated atomic species, and then the atom of the solid is referring to the crystal energy. So when it's free minus before it's free, then you will know that how much energy that is required. The electrostatic attractive force interaction between the negative charge electron and positive charge nucleus is the main force that contribute to cohesion in the solid. This force is strong if the atoms are far apart, but not too far apart too. So if the atoms are very close together, the electronic charge distribution of the atom will overlap, and the repulsive force between the electron will be the main force. So this is due to the Pauli exclusion principle, of which two electrons cannot have the same quantum number. Okay.